So we're given an equation that's t squared plus 3t. We're told to evaluate the integral of it from 1 to 4. So we know we have to set up an equation like this. The limit as n approaches infinity of this Riemann sum, the sum of f of si times delta t. Now our equation is actually called A in this. Not to be confused with this, which is A, our lower bound, or our left-hand bound. So let's start with delta t. We know that it's this upper bound B minus the lower bound A, not the equation A, over n. So that's going to be 4 minus 1 over n, or 3 over n. So we can replace this with 3 over n. Now we also know that S of I is going to be equal to A plus I delta t. Now our A, unlike other problems we've done so far, is not 0, it's 1. And then our delta t is 3, so it's going to be 3i over n. So now we have this, let me rewrite that. A of 1 plus 3i over n. So now our next step is to plug in 1 plus 3i over n into this equation right here every place there's a t. And use that for a of 1 plus 3i over n. So the limit as n approaches infinity of the sum is equal to 1 plus 3i over n squared plus 3 times 1 plus 3i over n, and that's all being multiplied by delta t, which is 3 over n. So when you multiply all this out, what you're going to get is this 27 I squared over n cubed plus 45 I over n squared plus 12 over n. So now what you want to do is split these up into different, 3 different summations, and have the i's by themselves inside the summation bring this stuff outside the summation. Except here you're going to have the constant 12 inside and bring out the 1 over n. So we can rewrite this as 27 over n cubed times the sum of I squared plus 45 over n squared times the sum of I plus 1 over n times the sum of 12. Or you could, what you could do, since this delta t is over here, you could bring this 3 over here and write a 4, and I think that's how you actually do it. In this problem, it really doesn't matter. You're going to end up getting the same answer. So now what we're going to do is we know what this is equal to, and this is equal to from the lesson. Those are always going to be the same. So now we just substitute those in and substitute in. The sum of a constant is that constant times n, so now we're going to substitute all that in. Alright, so this is the last step we just had. Now we're plugging in these values. It's going to be the limit as n approaches infinity, 27 over n cubed times n plus 1 times 2n plus 1 over 6. And again, that's something that's just a normal value. That's always going to be the same. Next is plus 45 over n squared times n plus 1 over 2. And then we're going to have 12 over n times n, because this is going to be the sum of 4 is going to be 4 times n. So these cancel out, and that's just 12. And now we're going to multiply all this out. And what you end up getting is the limit as n approaches infinity of 63 n squared plus 72n plus 9 over 2n squared. When you multiply all this out, that's what you get. So now we're going to divide all these things, all these 4 terms by n squared, so we can get a limit that we can actually solve. And when you do that, you're gonna, that's gonna go away, that's gonna go away. This is gonna become 72 over n, and this is gonna become 9 over n squared. And so the limit of some constant over infinity is 0. So both those are 0, and we're left with 63 over 2 plus 12, which is going to be equal to 87 over 2, or 43.5, and that is our answer.